What if I told you the ideas shaping our modern world weren't entirely ours? That centuries, even millennia before the first airplane took flight or the first computer powered on, ancient minds had already dreamed them into existence. It's a truth that bends time itself, from the soaring sketches of Leonardo da Vinci's helicopter to the intricate clockwork devices of ancient Greece. Humanity's greatest innovations were often foreshadowed in the unlikeliest of places. Today, we're unraveling one of history's most mesmerizing mysteries. 25 times ancient cultures predicted modern technology. Picture this, a world without blueprints, without silicon chips, without the tools we take for granted. And yet, somehow, visions of the future flickered in the minds of those who walked the earth thousands of years ago. How did they do it? Was it intuition, genius, or something even more extraordinary? From the steam-powered toys of Hellenistic inventors to the cryptic astronomical calculations of the Maya, these weren't just lucky guesses. They were glimpses into possibilities that would take centuries to materialize, and what's even more astonishing, many of these ideas weren't mere fantasies. They were detailed, functional concepts waiting for the right moment in history to come alive. This isn't just a story about machines or gadgets. It's about the boundless imagination of the human spirit, the same spark that drives us today. Think about it. Every time you send a text, board a plane, or even glance at a clock, you're touching the echoes of ancient ingenuity. So let's journey together across time and continents to uncover the startling moments when the past reached into the future. By the end, you'll see history and the modern world in a way you never expected. Ready to step into the mystery, the Antikythera Mechanism isn't just an artifact, it's a time capsule of genius. Discovered in a shipwreck off the coast of Greece in 1901, this intricate bronze device, dating back to around 100 BC, shatters every assumption about ancient technological limits. At first glance, it looked like a corroded lump of metal, but when researchers peered beneath the surface, they found something astonishing. A complex system of interlocking gears, precisely calibrated to track celestial movements with near-perfect accuracy. Think of it as the world's first analog computer, a machine that could predict solar eclipses, chart the positions of the sun and moon, and even forecast the dates of the Olympic Games. What makes this device so groundbreaking? Its design rivals the sophistication of 18th century clockwork. Tiny gear teeth, some as thin as a millimeter, meshed together to model the erratic motions of the planets, a problem so complex it wouldn't be solved again until the invention of modern mechanical calculators over 2,000 years later. The mechanism didn't just tell time, it mapped the heavens, turn a handle, and dials would spin to reveal the exact phase of the moon, the timing of lunar eclipses, and even the positions of 5 known planets. This wasn't guesswork, it was precision engineering, built by hands that understood the cosmos in ways we're only beginning to appreciate. And here's the most haunting question: how many minds like this were lost to history? The Antikythera Mechanism survived by pure chance, preserved in the silence of the sea. If this one device could slip through the cracks of time, what other marvels vanished without a trace? It's a reminder that innovation isn't linear, that brilliance can flicker in the dark, centuries ahead of its time, waiting for the world to catch up. Long before the Industrial Revolution transformed the world with steam-powered factories and locomotives, an inventor in 1st century Alexandria was already harnessing the same force. Hero of Alexandria, a visionary whose creations seemed to leap centuries ahead of their time. Among his many marvels was the Elipile, a device so simple yet revolutionary it could have rewritten history. Imagine a hollow metal sphere mounted on a boiler with 2 curved nozzles protruding from its sides. When heated, steam would shoot from these nozzles, causing the sphere to spin rapidly, a rudimentary steam turbine in action. This wasn't just a toy, it was proof that the ancients understood the principles of steam power 1,500 years before James Watt's famous improvements made it the backbone of modern industry. Hero's design was more than a curiosity, it was a blueprint. The Eolipile operated on the exact same principles as later steam engines. Expanding steam creates motion. Yet while Industrial Revolution engineers used this knowledge to drive pistons and turn wheels, Hero's invention remained largely an amusement, a dazzling demonstration for temple visitors rather than a tool to reshape society. Historians still debate why this technology wasn't scaled up. Was it a lack of materials, social priorities, or simply that no one yet saw its world-changing potential? The contrast is striking. The same force that later powered trains and factories sat quietly for millennia, trapped in a metal sphere spinning idly in the steam. But what if it hadn't been? Picture an alternate timeline where Hero's device sparked an ancient industrial revolution. The gears of progress might have turned far earlier, accelerating human innovation by centuries. The Eolipile stands as a haunting reminder of how close, and yet how far the ancient world came to leapfrogging into modernity. It wasn't a lack of ingenuity that held them back. The spark was there, flickering in the workshops of Alexandria, waiting for someone to fan it into flame. Buried beneath the sands of modern-day Iraq lay a mystery that could rewrite the history of electricity, the Baghdad Battery. Dating back to the Parthian Empire around 2,000 years ago, this unassuming clay jar, roughly the size of a fist, contained components that seem ripped from an ancient science experiment. A copper cylinder, an iron rod, and traces of acidic residue like vinegar or wine. When filled with an electrolyte liquid, this simple arrangement generates a small but measurable electric current, up to 2 volts. That's enough to power a faint glow in a modern LED, or more intriguingly, to electroplate gold onto silver. Archaeologists stumbled upon these artifacts in the 1930s, baffled by their purpose. Some dismissed them as storage vessels for scrolls, but the evidence tells a different story. Recreations by researchers like Dr. Arne Egebrecht in the 1970s demonstrated their electrochemical potential. Filled with grape juice as a natural acid, the jars produced enough current to deposit a thin layer of gold onto a statue, a technique still used in jewelry making today. Could the Parthians have been gilding ornaments with electricity centuries before Galvani's frog legs twitched in the 18th century? The experiments suggest it's not just possible but plausible. Yet the true genius of the Baghdad Battery lies in its simplicity. Unlike the Antikythera Mechanism's intricate gears or Hero's steam experiments, this technology required no moving parts, just an understanding of chemical reactions. Ancient Mesopotamians were already masters of metallurgy. Pairing that knowledge with electroplating would explain the flawless gold coatings found on artifacts from the era. But here's the twist: no electroplated objects have been definitively linked to the batteries themselves. Were they one-off experiments, ritual objects, or part of a broader, lost tradition? The silence of the historical record amplifies the mystery. If these were indeed batteries, why didn't the technology proliferate? Perhaps, like Hero's steam engine, it remained a curiosity, a spark of potential that never ignited a revolution. Or maybe we've only found fragments of a larger puzzle, with other applications lost to time. Either way, the Baghdad Battery forces us to reconsider the boundaries of ancient innovation. In a world without light bulbs or motors, someone, 2 millennia ago, held the power to harness electrons in the palm of their hand. Hero of Alexandria strikes again, but this time not with steam power or mechanical wonders. Picture walking into an Egyptian temple around 10 CE, dropping a coin into a slot, and watching as a stream of holy water miraculously flows into your cup. This wasn't magic, it was engineering. Hero's coin-operated dispenser wasn't just a clever party trick, it was the world's first vending machine, a concept so familiar today that it feels almost mundane. Yet here's the twist: the mechanism behind it was anything but ordinary. The device worked with elegant simplicity. A worshipper would insert a coin into the slot where its weight would press down on a lever. This lever, in turn, opened a valve just long enough for a precise amount of holy water to pour out before the coin slid off, resetting the system. No electricity, no microchips, just gravity and ingenuity. What's staggering is how closely this mirrors the basic principles of modern vending machines. Swap the holy water for a soda can, and the core function remains unchanged. Insert currency, trigger a mechanism, receive a product. But why invent such a thing? Some historians speculate it was about fairness, ensuring every worshipper received an equal measure of sacred water without human bias or waste. Others suggest it was a theatrical flourish, blending devotion with spectacle to awe temple visitors. Either way, Hero's design reveals a mindset startlingly modern: automation as a solution to everyday problems. Here's the real question gnawing at historians. If the ancients could automate holy water, why didn't this spark a broader revolution in self-service technology? The answer might lie in context. Without mass production or consumer culture, there was little demand for automated goods, no snack factories or subway stations clamoring for instant access. Hero's machine was a brilliant outlier, a glimpse of a future that wouldn't materialize for another 1800 years. Yet its legacy lingers. Next time you punch a button for a coffee or hear the clink of change in a modern vending machine, remember, you're not just activating circuits. You're participating in a ritual older than the Colosseum, one that began with a whisper of holy water and the clatter of ancient coins. The docks of ancient Rome should have crumbled centuries ago. Battered by waves, corroded by salt, exposed to the relentless Mediterranean sun, these structures faced conditions that would destroy modern concrete in decades. Yet walk through the ruins of Portus today, and you'll find 2,000-year-old piers still standing, their surfaces bearing the scars of time but their bones unbroken. The secret, a recipe lost to history, then rediscovered in modern labs: self-healing concrete. Roman engineers mixed their mortar with a shocking ingredient: volcanic ash from the Pozzuoli region. When combined with lime and seawater, this ash triggered a chemical reaction modern scientists call pozzolanic crystallization. As tiny cracks form from stress or erosion, seawater seeping in reacts with the ash to form new mineral deposits, effectively filling the gaps. It's a microscopic repair crew working autonomously for centuries. Modern experiments prove it. Samples of Roman concrete submerged in seawater for 9 months showed a 25% increase in compressive strength as these healing crystals grew. What's astonishing isn't just the durability, it's the intentionality. This wasn't accidental chemistry. The Romans specifically sought out volcanic ash, shipping it across the empire to build harbors from Caesarea to Alexandria. They knew it worked, even if they didn't understand the atomic dance behind it. Today, engineers are racing to replicate this ancient wisdom. MIT researchers have created synthetic versions using volcanic rock and a similar lime mixture, while other teams embed bacteria in modern concrete that excretes calcite to mimic Rome's self-repair. The irony is profound. Our best hope for future-proofing bridges and seawalls lies in decoding a 2-millennia-old innovation. Roman concrete didn't just resist time, it collaborated with it, turning the very elements that should destroy it into tools for renewal. As climate change threatens coastal infrastructure, this ancient technology whispers a solution. The past didn't just predict the future, it built a blueprint we're only now learning to read. In the year 132, as Rome's concrete harbors stood unshaken by time, another civilization was solving a problem that still plagues us today: how to detect earthquakes before they strike. Enter Zhang Heng, a polymath of China's Han Dynasty, whose invention wasn't just ahead of its time, it was eerily precise. His seismoscope, a bronze vessel adorned with 8 dragons, each poised above a corresponding frog, looked more like a ritual artifact than a scientific instrument. Yet when the Earth trembled hundreds of miles away, this device could point to the quake's direction with uncanny accuracy. Here's how it worked. Inside the ornate vessel hung a pendulum delicately balanced. When seismic waves arrived, the pendulum would sway, triggering a mechanism that released a ball from one of the dragon's mouths into the waiting frog below. The direction of the fallen ball revealed the earthquake's epicenter. In one famous account from 138, the device detected a quake west of Loyang, a region no one had felt shaking. Days later, messengers arrived confirming the event, proving the seismoscope's precision over distances modern seismologists would deem impressive even today. What makes Zhang Heng's design so revolutionary isn't just its functionality, it's the physics it harnessed. Modern reconstructions suggest he understood principles of inertia centuries before Newton's laws. The pendulum's movement mirrors how contemporary seismometers detect primary waves, the fastest seismic signals. Yet, unlike today's electronic sensors, this was pure mechanics, a masterpiece of leverage and gravity. Historians debate the exact inner workings, whether it used toothed gears, springs, or liquid mercury, but the outcome was undeniable, a tool that bridged art and science. The legacy of this invention lingers in unexpected ways. While no original seismoscopes survive, the concept inspired Arab scholars like Al-Kindi in the 9th century and European inventors during the Renaissance. Even now, the dragon and frog motif appears in modern seismic education as a symbol of early innovation. But the deeper question remains, how many other seismic events slipped past the historical record because no one thought to look for their echoes in bronze and symbolism? Zhang Heng's seismoscope wasn't just a detector, it was a declaration. In a world where earthquakes were often seen as divine wrath, his device framed them as measurable phenomena. That shift in perspective from supernatural to systematic might be its most enduring gift. Today, as satellites and algorithms predict disasters, we're still chasing the same goal Zhang Heng pursued 2 millennia ago, not just to survive the Earth's tremors, but to anticipate them. Damascus steel wasn't just a weapon, it was a mystery written in folded metal. For centuries, the legendary swords of the medieval Middle East were renowned for their impossible sharpness, their blades shimmering with watery patterns that seemed to dance in the light. Warriors whispered that these swords could slice through a falling silk scarf or shatter lesser blades with a single strike. But it wasn't magic that gave them their strength, it was an accidental marvel of nanotechnology, centuries before the word even existed. Modern scientists peering through electron microscopes made a jaw-dropping discovery. The steel contained carbon nanotubes, structures so advanced we only learned to engineer them in labs a few decades ago. The secret lay in the forging process, a technique lost to time. Blacksmiths of the era would repeatedly heat, hammer, and fold the steel, sometimes hundreds of times, blending iron from India with trace elements from Sri Lankan ore. This painstaking process didn't just remove impurities, it created a microscopic lattice of carbide nanowires and nanotubes, reinforcing the metal like rebar in concrete. X-ray studies reveal these nanotubes acted as natural shock absorbers, preventing cracks from spreading while maintaining an edge so sharp it defied explanation. Even more astonishing, some blades showed evidence of cementite nanowires, a brittle material that, when embedded just right, gave the steel both flexibility and hardness, a combination modern metallurgists still struggle to perfect. Why does this matter today? Because Damascus steel represents a happy accident of material science, a fluke of chemistry and craftsmanship that predated modern understanding by nearly 1,000 years. Contemporary researchers are now reverse engineering these techniques, hoping to unlock secrets for everything from bulletproof vests to next-generation aerospace alloys. The irony is palpable. We're using 21st-century tools to decode the craftsmanship of 8th-century smiths who had no idea they were nanotechnology pioneers. But here's the haunting twist: we still can't fully replicate it. The exact recipe vanished with the decline of the trade in the 18th century. modern attempts, even with precision furnaces and pure materials, produce blades that mimic the patterns but lack the legendary performance. Some theorize it was trace impurities in the original ores, vanadium or chromium, that catalyzed the nanotube formation. Others believe the key lies in the rhythmic hammering, a mechanical alchemy we've yet to quantify. What remains is a testament to human ingenuity. Those medieval smiths weren't just making weapons, they were bending the atomic structure of steel without knowing it. Every ripple in a Damascus blade is a fossilized echo of their unknowing genius, a reminder that sometimes the most advanced technologies aren't invented, they're discovered, hidden in plain sight, waiting for the right eyes to see them. High in the jungles of Mesoamerica, where howler monkeys drowned out the sounds of civilization, Mayan astronomers gazed at the stars with a precision that defies belief. Without telescopes, without silicon chips, they mapped the cosmos with such accuracy that their calculations still stand up to scrutiny today. Take their Hob calendar, a solar-based system that tracked 365 days with an error margin of just 1 day every 6,140 years. To put that in perspective, our modern Gregorian calendar drifts by 1 day every 3,300 years. The Maya weren't just counting days, they were calibrating time itself on a scale most computers would envy. But their true masterpiece lay in decoding Venus. While medieval Europe still debated whether the Earth was flat, Mayan scribes had already calculated the planet's synodic period, the time it takes to return to the same point in the sky, as 583.92 days. NASA modern measurement 583.92. That's not a coincidence, it's computational genius. Hidden within the Dresden Codex, a bark paper book surviving centuries of humidity and conquest, are tables predicting Venus's movements half a millennium in advance, down to intervals matching our astronomical software. These weren't rough estimates, they accounted for the planet's erratic retrograde motion, a celestial dance most cultures wouldn't comprehend for another 1,000 years. How did they achieve this? The answer lies in obsession. Generations of scribes, likely working in observatories like El Caracol at Chichen Itza, meticulously recorded celestial events on towering stone stelae. They cross-referenced lunar cycles, solar years, and planetary positions with a decimal number system based 20 math that let them handle enormous calculations. Their long count calendar could pinpoint dates millions of years in past or future, a scope that makes our Y2K panic seem quaint. Yet the most chilling detail isn't their accuracy, it's their purpose. Unlike Western astronomy driven by navigation or physics, the Maya saw time as a living, sacred force. Venus wasn't just a planet, its appearances signaled wars, droughts, or the rise of kings. Their calculations weren't academic, they were survival tactics, attempts to align human fate with the rhythms of the cosmos. Today, as our satellites orbit Venus and AI crunches exabytes of sky data, we're still chasing what the Maya knew, that the universe isn't just something to observe, but a language to decipher, one they began translating when Europe was still in shadows. Archimedes' legendary death ray stands at the crossroads of myth and physics, a weapon so audacious it feels ripped from science fiction. Ancient historians like Lucian and Galen described Syracuse's defense during the Roman siege of 212 BC, where the brilliant mathematician allegedly orchestrated an optical onslaught. Bronze shields polished to a mirror finish were said to focus sunlight into a searing beam capable of igniting Roman ships hundreds of feet away. The concept echoes eerily with modern directed energy weapons like lasers, raising a tantalizing question. Could a 3rd century BC genius have harnessed light as a weapon centuries before the physics to explain it existed? Experiments both validate and complicate the legend. In 2005, MIT students attempted to recreate the death ray using 127 mirrored tiles. Under ideal conditions, clear skies, stationary targets, they succeeded in setting a wooden boat aflame after 10 minutes of sustained focusing. A decade later, the TV show Mythbusters tried multiple configurations, failing to achieve combustion but acknowledging that smoke could be produced, potentially panicking crews. The discrepancy hinges on variables ancient sources omit. Were the mirrors parabolic for tighter focus? How coordinated were the operators? Even skeptics admit the principal work's solar furnaces today reach temperatures over 3,000 degrees Fahrenheit using the same basic idea. What's often overlooked is Archimedes' deeper mastery of optics. His treatise on burning mirrors, though lost, was cited by Arab scholars for its geometric precision in describing reflection. He'd already calculated ways to maximize light concentration mathematically, suggesting the death ray wasn't just wartime improv, it was applied theory. Modern engineers note that Syracuse's geography could have amplified the effect. Midday sun reflecting off the sea, ships moored within optimal range, and shields angled from curved fortifications. Yet the true stroke of genius lies in the psychology. Imagine the terror of sailors watching their vessels smolder from an invisible force, a God's wrath made tangible. Whether the flames were literal or exaggerated, the weapon's reputation alone became a deterrent, buying Syracuse precious time. Today's military researchers still study the episode, not for its practicality but for its innovation. The death ray represents perhaps the first recorded attempt to weaponize pure science, transforming geometry into a tactical advantage. The debate endures because it crystallizes a timeless truth. Archimedes' mind operated on a plane others wouldn't reach for millennia. Even if the details blurred over centuries, the underlying vision, controlling light as a tool, proved prophetic. From laser defense systems to solar satellites, we're still chasing the promise he glimpsed in the glare of bronze and Mediterranean sun. Deep in the crypts of Egypt's Dendera temple, where hieroglyphs stretch across sandstone like a frozen river of symbols, one carving stops visitors dead in their tracks. It shows a surreal scene, a massive bulb-like object with a coiled serpent inside, supported by a pillar and connected to what looks like cables. To some, this isn't just sacred art, it's a blueprint. The so-called Dendera light has sparked theories that ancient Egyptians might have harnessed electricity, painting their tombs not by torchlight but by the glow of primitive lamps. The comparison is hard to ignore. The bulb-shaped object bears an uncanny resemblance to a Crookes tube, an early electrical component that produces light when voltage is applied. The cables snake toward a box eerily reminiscent of a power source, while the serpent inside the bulb mirrors the twisting filament of a modern light bulb. Could this be evidence of lost technology? Proponents point to the absence of soot in certain tombs, asking how artists could have painted intricate murals in pitch darkness without leaving traces of smoke. But here's where the mystery deepens. Modern engineers have tried to recreate the Dendera light as a functioning device, using materials available to ancient Egyptians: copper, batteries modeled after the Baghdad artifacts, and brine as an electrolyte. Some experiments have produced faint illumination. Yet critics argue the hieroglyph is more likely a symbolic representation. The bulb aligns with known depictions of the lotus flower, a sacred symbol of creation, while the serpent matches the god Harsomptus emerging from a cosmic egg. Even the cables could be stylized lotus stems common in Egyptian iconography. The debate hinges on context. Electricity, as we know it, requires a system: generators, circuits, insulation, none of which appear in the archaeological record. But consider this: if the carving isn't a literal lamp, why place it in a pitch-black crypt where its details would be invisible without artificial light? The temple itself was a hub of advanced knowledge, with priests who understood astronomy, chemistry, and geometry. Could they have stumbled upon a fleeting electrical phenomenon, later encoded in myth? Perhaps the truth lies between extremes. The Dendera light might not prove ancient Egyptians had working light bulbs, but it reveals something equally profound: their ability to conceptualize the impossible. In those carved lines, we see a civilization dancing on the edge of discovery, wrapping cutting-edge ideas in the language of symbolism. Whether the image represents divine metaphor or dimly remembered technology, one thing is clear: the human imagination has always reached for the switch to illuminate the unknown. The sea burned before ships ever reached the battlefield, a liquid hellfire that clung to wood and flesh alike, impossible to extinguish even in water. This was Greek fire, the Byzantine Empire's most closely guarded secret, a weapon so devastating it shaped naval warfare for centuries. First deployed in 672 CE against Arab fleets besieging Constantinople, its formula remains lost to history, but its impact echoes in modern warfare's incendiary arsenal. Imagine a substance sprayed from bronze tubes mounted on ships, igniting upon contact with air, burning even on waves, a medieval napalm that turned the Mediterranean into a theater of terror. What made Greek fire so revolutionary was its delivery system. Byzantine sailors used pressurized siphons akin to early flamethrowers to project streams of fire over 100 feet. Contemporary accounts describe the horror of crews trapped by flames that water only spread, forcing men to jump into the sea rather than face combustion. The mechanics were shockingly advanced. A boiler heated the mixture, while a pump, likely based on ancient piston designs, forced it through nozzles where a lit fuse ignited the spray. This wasn't just tossing fire, it was precision-engineered combustion, a predecessor to the flamethrowers of World War I and the incendiary bombs of World War II. The chemistry is still debated, but clues point to a volatile cocktail. Historians speculate it contained crude petroleum from the Black Sea's natural seeps, mixed with quicklime for self-ignition and pine resin for adhesive properties. Some accounts suggest saltpeter or sulfur, hinting at an early gunpowder-like composition. The Byzantines called it liquid fire, but its behavior aligns eerily with modern napalm's sticky, oxygen-starved burn. Even the countermeasures vinegar or urine-soaked hides mirror tactics used against 20th century flamethrowers, yet the true genius lay in its secrecy. Emperors protected the formula like a state secret, with only a few families entrusted with its production. When enemies captured Greek fire supplies, they couldn't replicate it. The knowledge died with Byzantium's fall. Modern labs have tried for centuries to reverse engineer it, but the closest approximations still lack the original's reported intensity and water resistance. What's often overlooked is the psychological warfare. Greek fire wasn't just a tool, it was a specter. The mere rumor of its deployment could scatter fleets. Its glow against nighttime waves became a deterrent as powerful as any nuclear threat today. In that sense, Byzantium's invention wasn't just ahead of its time. It pioneered the concept of weapons so fearsome their reputation alone could sway battles. The legacy lingers in grim ways, from the flamethrowers of Okinawa to the incendiary gels used in modern combat. The principles of Greek fire endure. It's a sobering reminder: some technologies, once unleashed, never disappear. They simply evolve, carrying forward the ancient imperative to harness fire not just as a tool, but as a weapon that reshapes the boundaries of war. The stones of Machu Picchu don't just sit together, they dance. When earthquakes ripple through the Andes, these massive polygonal blocks shift and settle, then return to their original positions as if guided by an unseen hand. This isn't magic, it's masterful engineering. The Incas built their cities without mortar, carving each boulder with such precision that a knife blade couldn't slip between them. Yet what seems like aesthetic perfection is actually a seismic survival strategy, a design so advanced it's inspiring modern architects to rethink how we earthquake-proof our cities. Take a closer look at these walls. The jigsaw-like seams aren't random. Each irregular angle disperses seismic energy in multiple directions, preventing cracks from propagating. Unlike rigid modern concrete, which fractures under stress, the stone's slight movements absorb shocks like a suspension system. Some interiors even feature trapezoidal doorways and inward-leaning walls, funneling energy downward into the foundation. The result, structures that have withstood 500 years of tremors in one of the most tectonically active regions on Earth. Contemporary engineers are now decoding these ancient secrets. Laboratories use laser scans to analyze how the stone's uneven surfaces create friction, mimicking the asperities in fault lines that reduce slippage. In Japan, researchers combined Inca principles with modern materials to develop seismic invisibility cloaks, foundations that deflect vibrations around buildings. Meanwhile, Peruvian architects are reviving these techniques in new constructions, proving that sometimes the best way forward is to look back. But here's the real marvel: the Incas achieved this without metal tools or written language. Their masons relied on trial and error, passing down knowledge through generations of hands-on practice. Modern simulations show their walls could endure quakes up to 7.5 magnitude, comparable to today's best seismic codes. Yet while we rely on steel rebar and rubber bearings, the Incas used geometry alone. Their legacy whispers a radical idea: that resilience might not come from overpowering nature, but from learning to move with it. The stones of Cusco and Ollantaytambo aren't just ruins, they're living classrooms. As cities from San Francisco to Tokyo grapple with rising seismic threats, these ancient walls offer a lesson written in granite. Sometimes the most futuristic solutions are carved in the bedrock of the past. Standing in the heart of Delhi's Qutub complex, a 7-ton iron pillar has baffled scientists for centuries. Built in the 4th century CE, this towering relic of the Gupta Empire hasn't rusted in over 1,600 years, a feat modern metallurgy still struggles to replicate. At first glance, it seems impossible. Iron, exposed to monsoons and pollution, should have crumbled to dust long ago. Yet here it stands, smooth as the day it was forged, its surface bearing only the faintest patina. The secret, a recipe locked in its atomic structure, an alloy so advanced it predates the scientific method by a millennium. Modern spectrographic analysis reveals the pillar's magic lies in its phosphorus content. Unlike contemporary iron, which prioritizes purity, the Gupta metalworkers intentionally blended their iron with high phosphorus levels, nearly 1% by weight. This wasn't a flaw, it was genius. Under the microscope, the pillar's surface shows a thin, continuous film of iron hydrogen phosphate hydrate. This microscopic shield, just 50 to 60 nanometers thick, acts like an invisible cloak against oxygen and moisture, preventing the electrochemical reactions that cause rust. Even more astonishing, the alloy's phosphorus actually migrates to the surface over time, constantly renewing this protective layer like a self-repairing suit of armor. But here's the twist: this technology wasn't accidental. Ancient Indian texts like the Artha Shastra describe sophisticated iron smelting techniques, including the use of specific wood types to introduce phosphorus during smelting. The pillar's creators likely understood their material's properties through generations of trial and error, passing down metallurgical knowledge as carefully as royal edicts. The irony is bitter today. We battle rust with chromium in stainless steel, an energy-intensive process, while the pillar whispers a simpler solution from the past. Debates still rage over why this innovation didn't spread. Some argue the high phosphorus alloy was too brittle for weapons, limiting its appeal to ceremonial pillars. Others suspect the technique was lost during invasions or guarded as a trade secret. Whatever the reason, the pillar's legacy is undeniable. NASA scientists now study its corrosion resistance for spacecraft, while Indian researchers experiment with replicating its alloy for bridges in humid climates. The pillar's true lesson isn't just about chemistry, it's about patience. While we chase stainless solutions with synthetic coatings and complex alloys, this ancient monument endures with quiet elegance, proving sometimes the most revolutionary technologies aren't the loudest. They're the ones that stand silently, waiting for the future to catch up. centuries before the skies of Europe trembled with the first gas-filled balloons, Chinese military strategists were already harnessing the wind not with wings but with fire and silk. Legend credits the ingenious Zhu Zhiliang, a chancellor of the Shu Han Kingdom during the Three Kingdoms period, with crafting the earliest hot air balloons around 225 CE. Known as Kongming lanterns, these delicate yet effective devices weren't toys, they were battlefield tools, designed to float distress signals over enemy lines or coordinate troop movements under the cover of darkness. Picture these lanterns hovering above ancient battlefields, paper-thin silk stretched over bamboo frames, with a small wax or oil flame heating the air inside. The physics was elegant. As the air warmed, it expanded, becoming lighter than the cooler atmosphere outside. This simple principle of buoyancy allowed the lanterns to rise, sometimes hundreds of feet, carrying messages or merely sowing confusion among rival forces. Unlike later European balloons that sought to carry passengers, Kongming lanterns prioritized function over spectacle. Their designs were lightweight, collapsible, and crucially, reusable, qualities modern military drones still emulate. But the real marvel lies in their longevity. While Western ballooning is often traced to the Montgolfier brothers' sheep and duck-laden flight in 1783, Chinese records suggest Kongming lanterns had been floating for over a millennium prior. Jesuit missionaries in the 17th century documented lantern festivals where hundreds would ascend simultaneously, dotting the night sky like a swarm of fireflies. These weren't just celebrations, they were demonstrations of an unbroken technological tradition, one that had refined lantern materials from silk to treated paper and optimized flame sources for longer flights. The gap between these ancient precursors and European ballooning raises a provocative question. Why didn't China develop manned flight earlier? The answer might lie in purpose. Kongming lanterns were tools, not transport. Their creators saw them as extensions of signal fires or carrier pigeons, not vessels for human exploration. Yet when the Montgolfiers finally unlocked the secret of scaled-up ballooning, they unknowingly echoed a principle mastered in the East centuries before. Proof that innovation often follows parallel paths separated only by time and intent. Today, Kongming lanterns endure as cultural symbols, released during festivals for luck. But their legacy soars higher. Modern hot air balloons still rely on the same thermodynamics Zhu Zhiliang harnessed, while aerospace engineers study their designs for microdrone applications. The next time you see a lantern drift into the night, remember, you're witnessing not just a tradition, but a fragment of flight's hidden history, whispering across 17 centuries. In the scorching deserts of ancient Persia, where summer temperatures could melt stone, engineers devised a cooling system so effective it still puts modern air conditioning to shame. These weren't primitive fixes, they were architectural masterpieces called wind catchers or badgers, towering above clay rooftops as early as the 6th century BC. Picture a slender chimney with vents facing the prevailing winds, designed not just to catch breezes but to manipulate physics itself. As hot air rushed in, it would funnel downward into the home's interior, passing over subterranean water channels or moist clay walls. The air would cool rapidly, sometimes by as much as 20 degrees Fahrenheit, before circulating through living spaces like a natural AC unit. The genius of wind catchers lay in their adaptability. Some were unidirectional, funneling cool night air into storage spaces to chill food. Others had multi-directional vents that could pivot to trap breezes from any angle. In cities like Yazd, entire neighborhoods were arranged to maximize airflow, with wind catchers acting as a communal cooling grid long before the concept of urban planning existed. Modern studies reveal their efficiency. When tested against electric air conditioners in Iran's central desert, traditional badgers used zero energy while maintaining comparable comfort levels, a sustainability benchmark today's engineers struggle to match. But the real innovation was in the details. Many wind catchers incorporated canats, underground aqueducts that further chilled incoming air through evaporation. Others featured internal baffles to slow airflow, increasing contact time with cool surfaces. The effect wasn't just physical, it was psychological. The sound of wind whispering through the towers became synonymous with relief, a sensory promise of comfort in the harshest climates. What's startling is how closely these ancient designs mirror modern passive cooling systems. Contemporary architects from Arizona to Dubai now study badgers for inspiration, replicating their principles in green buildings. The irony is palpable. While we pump refrigerants into the atmosphere, a 3,000-year-old technology offers a blueprint for carbon-neutral cooling. The Persians didn't just predict HVAC systems, they outdesigned them, proving that sometimes the most advanced solutions aren't invented but remembered. The floors of Roman villas were warmer than most modern homes, and they didn't need a single radiator. Step into the ruins of Bath, England, or Pompeii's aristocratic houses, and you'll find the ghosts of an ancient revolution in comfort, the hypocaust. This wasn't just heating, it was a thermodynamic masterpiece. Slaves or servants would stoke furnaces in courtyards, channeling hot air through a labyrinth of raised tile pillars supporting the floors above. The heat would rise gently, warming marble slabs to the perfect temperature for bare feet, while hollow walls lined with clay pipes carried warmth upward like an invisible embrace. The result, even heat distribution centuries before the term radiant flooring entered architectural lexicons. What's staggering isn't just the system's sophistication, it's its scalability. From modest townhouses to the sprawling baths of Caracalla, hypocausts adapted effortlessly. Engineers varied pillar height to control airflow, ensuring large spaces stayed uniformly warm while smaller rooms didn't overheat. Some villas even had adjustable flues, letting residents fine-tune temperatures room by room, a level of customization many modern homes still lack. The Romans didn't just invent central heating, they perfected its delivery, anticipating principles we'd rediscover in the 19th century. Modern radiators, by comparison, seem almost primitive. Their localized heat creates cold spots and wastes energy, whereas hypocausts enveloped spaces in consistent warmth. Today's radiant floor systems, popular in eco-conscious designs, are direct descendants of this ancient tech, swapping hot air for water-filled pipes but keeping the same core philosophy: heat from below, not beside. The irony, while we tout these systems as cutting-edge, Roman engineers had already crunched the math on thermal mass and conductivity, using materials like terracotta that retained heat for hours after fires died down. Yet the hypocaust's brilliance extended beyond physics. It reshaped social rituals. Public baths became hubs of politics and gossip precisely because they were comfortably warm year-round, a cultural shift akin to modern cafes with Wi-Fi. Patricians flaunted hypocausts as status symbols, with some even piping excess heat to warm outdoor pools. This wasn't just engineering, it was lifestyle design, blending utility with luxury in a way that feels strikingly contemporary. The system's decline after Rome's fall speaks volumes. Medieval Europe, losing the knowledge to maintain hypocausts, shivered through winters until the Industrial Revolution. But the idea never truly vanished. Korean ondol floors and Swiss stove heaters kept the principle alive, proving good design transcends eras. Now, as we seek sustainable alternatives to forced air systems, the hypocaust whispers a solution older than the Colosseum. Sometimes the warmest future lies buried just beneath our feet. Stretching across Peru's arid plains, the Nazca lines form a sprawling canvas of geometric shapes and towering figures, some stretching longer than a football field, others depicting animals so vast they can only be fully seen from the sky. For decades, these enigmatic drawings have sparked wild theories, from alien runways to celestial maps. But what if their purpose was startlingly practical? Imagine standing in the Nazca Desert 2,000 years ago, a traveler navigating treacherous trade routes with no landmarks in sight. Suddenly, you spot a massive trapezoid etched into the earth, its lines pointing toward a distant mountain pass. This wasn't just art, it could have been the ancient world's most ingenious navigation system, a prehistoric GPS etched into the desert floor. The layout of the lines tells a compelling story. Many converge at strategic points: mountain springs, fertile valleys, or intersections of ancient trade paths. Researchers like archaeologist Johann Reinhard have noted how certain geoglyphs align with water sources, vital for survival in one of Earth's driest climates. But the real clue lies in their visibility. While the full designs require altitude to appreciate, key segments are visible from ground level as stark, linear pathways. Walk along one, and it might lead you to a critical oasis or a safe crossing through the rugged terrain. The famous astronaut figure, for instance, sits near a steep incline, a potential warning to travelers or a marker for an alternate route. Modern experiments add weight to this theory. Drone surveys reveal that the line's trajectories match seasonal wind patterns, which ancient caravans likely used to predict safe travel windows. Even more intriguing, the mineral composition of the desert floor. The Nazca people scraped away dark surface stones to expose lighter soil beneath, creating contrast that would have glowed under moonlight or reflected heat differentially, making them detectable by temperature shifts, a feature that could have guided night travelers or even been spotted from distant ridges. Critics argue that the line's ceremonial role can't be ignored, and they're right. Many align with solstice sunrises or constellations, suggesting dual purposes. But this duality might be the point. Indigenous cultures often blended practicality with spirituality. Waypoints could also be sacred sites, their very functionality a divine gift. The Inca's sect system, a network of ritual pathways radiating from Cusco, operated similarly, mapping both physical and cosmic journeys. The Nazca line's enduring mystery isn't just about their creation, but their intent. In a world without maps or compasses, these geoglyphs may have been the ultimate multi-tool, part pilgrimage route, part trade guide, part celestial clock. Today, as satellites render physical navigation obsolete, the lines remind us that every civilization grapples with the same fundamental need to find its way, whether across deserts or through the stars. The desert still holds its secrets, but one thing is clear: the Nazca didn't just draw on the land, they coded it with directions, waiting for the right eyes to read them. Fierce Nordic winters brought weeks of overcast skies, conditions that would leave any sailor stranded without celestial bearings. Yet the Vikings routinely navigated the treacherous North Atlantic, reaching North America centuries before Columbus, with nothing but crude tools and an uncanny grasp of nature's hidden signals. Their secret, a seemingly ordinary crystal that turned daylight into a compass. Icelandic sagas mention solarstein, sunstones, that could reveal the sun's position even through dense fog or storm clouds. Modern experiments confirm these weren't myths. Calcite crystals, common in Scandinavia, exhibit a property called birefringence, splitting light into two beams. When rotated, the stone's brightness shifts depending on the sun's hidden position, creating a luminous X at the exact angle of sunlight piercing the atmosphere. Picture a Viking navigator holding a translucent calcite fragment up to the gloom. By tilting the crystal until both beams match in intensity, they'd pinpoint the sun's location with startling precision. A trick replicated by researchers in 2011 using a crystal found aboard a 16th century English shipwreck. Even on completely overcast days, this method can determine the sun's bearing within 5 degrees, accurate enough to guide longships from Norway to Newfoundland. The science is elegant. Sunlight scattered by clouds becomes polarized, a pattern invisible to human eyes but decipherable through calcite's double refraction. Vikings likely paired these stones with horizon boards, wooden discs marked with cardinal directions, creating a navigation system rivaling early magnetic compasses. What's often overlooked is the ingenuity behind their calibration. Without understanding polarization physics, Viking navigators mastered an empirical technique, passing down precise rotation and observation methods through generations. Archaeologists speculate they may have also used twilight cues, noting how the crystal's behavior changed at dawn versus dusk to refine their readings. Contemporary sailors, reliant on GPS, have tested sunstones as emergency backups, with some reporting they're more reliable than magnetic compasses near the poles, where Earth's magnetic field grows erratic. Yet the sunstone's true brilliance lies in its simplicity. Unlike fragile compasses susceptible to metal interference, calcite works indefinitely, immune to rust or misalignment. It's a reminder that advanced technology doesn't always mean complexity. Sometimes it's about seeing the world differently. As we now study these crystals for quantum computing applications, we're rediscovering what the Vikings knew all along: that nature's most powerful tools often come not crafted by human hands, but unearthed, waiting for the right mind to read their light. Centuries before the word robot entered our vocabulary, Greek engineers were already bringing inanimate objects to life. In the workshops of Alexandria and Athens between 400 and 200 BCE, inventors like Ctesibius and Philo of Byzantium crafted astonishing automata, mechanical servants, singing birds, and even entire theatrical performances powered by nothing but gears, levers, and the precise manipulation of air and water pressure. These weren't crude novelties, they were sophisticated prototypes of automation, blurring the line between art and engineering in ways that still resonate today. Take the famous automatic servant designed by Philo. This life-sized figure of a maiden stood holding a jug in one hand. When a visitor placed a cup beneath her, she would pour wine, then, as if sensing the cup was full, seamlessly switch to dispensing water. The mechanism relied on a clever counterweight system hidden in her base, with air pressure and carefully balanced reservoirs ensuring the liquids mixed only when intended. Modern engineers who have recreated the device describe it as a primitive feedback loop, an early example of machines responding to their environment, but the Greeks didn't stop at practical helpers. Their automata were also storytellers. In the theaters of Byzantium, audiences marveled at mechanical plays where puppets reenacted entire myths, ships sailing across miniature seas, gods descending from the heavens on hidden strings, and dragons whose jaws spewed real flames. Hero of Alexandria, the same genius behind the steam-powered Aeolipile, designed a self-moving puppet theater driven by weights and pulleys. His scripts weren't just plays, they were the world's first programmable performances, with scenes unfolding in precise sequences dictated by the machinery's rhythms. The closest modern equivalent, the animatronic shows of Disneyland, though Hero's designs required no electricity, just gravity and ingenuity. What's most striking is how these inventions mirrored philosophical debates of the time. Aristotle pondered whether tools could ever become autonomous, while myths like Pygmalion's living statue hinted at humanity's obsession with creating life. The automata weren't just toys, they were physical manifestations of these ideas, probing questions about agency and creation that still haunt our age of artificial intelligence. Yet the true masterpiece might be the hydraules, an automated water organ that played itself using a complex system of rotating drums studded with pins. As the drum turned, the pins triggered valves to release air into different pipes, producing melodies without a musician. This wasn't just an early player piano, it was a programmable music machine, its code etched into brass. Surviving texts suggest some hydrolyzers could even mimic birdsong or simulate thunderstorms, making them the ancient world's equivalent of a synthesizer. The legacy of these devices is more than historical curiosity. When you watch a robotic arm assemble a car or ask a smart speaker to play a song, you're glimpsing the same thread of innovation that once animated Greek workshops. The automata prove a profound truth. Technology doesn't evolve in a straight line. Ideas flicker into existence, fade, and rekindle centuries later in new forms. Those ancient engineers didn't just predict robotics, they laid its foundations, one gear at a time, in a world where the boundary between magic and machinery was still being drawn. Buried within ancient Sanskrit epics like the Mahabharata and Ramayana lie accounts so startling they've fueled debates for centuries. Detailed descriptions of aerial vehicles called vimanas, capable of soaring through the skies with precision and power. These weren't mythical chariots pulled by winged horses. They were technological marvels described with mechanical specifics that sound eerily familiar to modern aviation. The Vaimanika Shastra, a controversial early 20th century text purportedly based on older sources, goes further, outlining propulsion systems, navigation techniques, and even aerial combat strategies. Some translations mention mercury vortex engines, gyroscopic stabilization, and layered metal alloys, details that uncomfortably mirror cutting-edge aerospace engineering. The Samarangana Sutradhara, an 11th century text, dedicates an entire chapter to vimanas, classifying them by shape and function. Some were saucer-like Rukma, others cigar-shaped Tripura, with capabilities ranging from stealth cloaking to long-distance travel. One passage describes pilots wearing protective suits and using mirrors to absorb solar energy, while another speaks of aerial battles where vimanas deployed weapons resembling modern missiles. Skeptics argue these are poetic metaphors or later interpolations, but the consistency across texts raises questions. Why would multiple ancient authors independently invent such precise, technical accounts if there wasn't some kernel of observation or tradition behind them? Modern attempts to reconcile these descriptions range from the scholarly to the sensational. Aerospace researchers like Dr. J.B. Hare have noted parallels between vimana propulsion systems and hypothetical anti-gravity concepts explored by NASA. Others point to the discovery of high-temperature crucibles and advanced metallurgy in Indus Valley sites, suggesting the ancients possessed materials science capable of supporting lightweight, heat-resistant structures. Meanwhile, critics highlight the Vaimanika Shastra's disputed origins, its rediscovery via psychic channeling in the 1920s, as evidence of historical fabrication. Yet the most compelling clues might lie in India's architectural wonders. The stepwells of Chand-Bayori, with their intricate, almost aerodynamic symmetry, and the acoustic precision of temples like Vitala suggest a culture deeply attuned to physics and engineering. Could Vimana accounts be garbled records of real but lost technologies like Damascus steel or Greek fire, or do they reflect something more profound, a symbolic language encoding spiritual concepts through mechanical metaphors? The Vimana enigma forces us to confront the limits of historical interpretation. In a world where oral traditions carried knowledge across millennia, how much innovation might have flickered into existence and vanished without a trace? Whether these texts describe physical machines or imaginative leaps, they undeniably prove one thing: the human fascination with flight isn't a modern obsession. It's a dream as old as civilization itself, whispered across time in the language of myth and metal. The woman buried in a Theban tomb around 1000 BC walked differently in death than she had in life, not because of injury but because of innovation. When archaeologists uncovered her mummy in the 1990s, they found something astonishing strapped to her right foot: a meticulously carved wooden toe, complete with a hinged joint and wear marks suggesting years of use. This wasn't a ceremonial addition. It was a functional prosthetic, engineered with such precision that modern amputees who have tested replicas report near-natural mobility. Imagine a 3,000-year-old device so advanced it could rival 20th-century limb replacements, a fusion of carpentry and biomechanics that rewrites the history of medical technology. What sets this toe apart from other ancient prosthetics is its ergonomic design. Crafted from linden wood and reinforced with leather straps, the contour matches the human foot's anatomy with subtle curves that distribute weight evenly to prevent blisters. The hinge, made of durable fibers, allowed for fluid motion during walking, while the angled tip mimicked the push-off action of a real toe. Researchers at the University of Manchester even commissioned a replica, testing it with volunteers missing the same digit. The results: the ancient design reduced pressure on the ball of the foot by nearly 30%, proving it wasn't just cosmetic, it restored function. But here's the real revelation: the toe shows signs of iterative improvement. Microscopic analysis reveals multiple layers of resin and plaster, suggesting adjustments were made over time to perfect the fit. This wasn't a one-off experiment, it was refined technology, likely backed by generations of artisan knowledge. Egyptian medical texts like the Edwin Smith Papyrus already detailed sophisticated surgical techniques, so the leap to prosthetics aligns with their mastery of the body's mechanics. The toe's owner, possibly a priest's daughter or a noblewoman, would have needed this device for more than vanity. Walking barefoot on stone floors or uneven terrain without it could have been agonizing. Modern prosthetics, with their carbon fiber and microprocessors, might seem light years ahead, but the principles remain strikingly similar: comfort, mobility, and durability. The same challenges Egyptian artisans solved with wood and leather still drive engineers today. Even the psychological aspect resonates. The toe was stained to match skin tone, hinting at an ancient understanding of the user's emotional needs. The broader implications are profound. If prosthetics existed this early, how many other medical advancements have been lost to time? The Theban toe forces us to reconsider the boundaries of ancient innovation, proving that compassion and ingenuity have always walked hand in hand, or in this case, toe in sandal. The Greeks may have given us the word trigonometry, but the Babylonians mastered its principles over a millennium earlier, and they did it with nothing but clay tablets and a base 60-number system. In the dusty archives of Columbia University rests Plimpton 322, a palm-sized clay tablet dating back to 1800 BC. At first glance, its neat cuneiform columns look like an ordinary ledger, but this little slab of baked earth contains the world's oldest trigonometric table, a mathematical marvel so precise it could calculate the sides of a right triangle with accuracy rivaling modern calculators. Deciphering Plimpton 322 wasn't easy. When archaeologists first uncovered it in the early 1900s, they assumed it was just another administrative record. But mathematician Otto Neugebauer's analysis in the 1940s revealed something extraordinary. The tablet lists 15 perfect Pythagorean triples, sets of whole numbers that satisfy the famous a squared plus b squared equals c squared theorem, like 3, 4, 5 or 5, 12, 13. The kicker: these weren't random. The triples were systematically ordered by angle, creating a ratio-based trigonometric table more intuitive than anything the Greeks would devise centuries later. What makes this tablet revolutionary isn't just its age, it's its methodology. Unlike Greek trigonometry, which relied on angles and circles, the Babylonian approach was purely algebraic. Their base 60 system allowed for fractions far more precise than Greek or Roman numerals, enabling calculations like the square root of 2 accurate to 6 decimal places. Historians like Dr. Daniel Mansfield suggest the tablet was a teacher's aid, possibly used for surveying or constructing temples. Flip it sideways and the numbers align with slope ratios for ramps or roofs, proving this wasn't abstract math, it was applied engineering. Modern experiments underscore its brilliance. Researchers at the University of New South Wales recreated the tablet's calculations using only period-appropriate tools, reed styluses and clay, confirming the Babylonians could derive these triples through clever number theory. They likely used a technique involving reciprocal pairs, exploiting patterns in their sexagesimal system to generate accurate results without modern notation. The implications are staggering. Centuries before Pythagoras was born, Mesopotamian scribes had not only discovered his theorem but built a working toolkit around it. So why did Greek trigonometry dominate history while Babylonian math faded? Part of the answer lies in transmission. When Alexander the Great burned Persepolis, countless clay tablets were lost or scattered. Greek mathematics, recorded on more durable parchment, spread through Europe, while Babylon's legacy crumbled into shards waiting for archaeologists to reassemble them. But perhaps the greater irony is how contemporary this ancient system feels. Plimpton 3:22's ratio-based approach mirrors modern rational trigonometry, a field rediscovered in the 21st century. The tablet's silent lesson resonates today. Progress isn't always linear. Sometimes the most advanced ideas lie buried for millennia, waiting for the world to circle back and recognize their genius. In those cuneiform marks, we see not just numbers, but a testament to the universality of human curiosity, the same drive that now sends probes to Mars and unlocks quantum algorithms. The Babylonians didn't just predict trigonometry, they reinvented it, proving that brilliance isn't bound by epochs. It simply awaits the right moment to be unearthed. In the year 132 CE, a violent earthquake struck China's Henan province, leveling towns and killing thousands. Days later, court officials reported something unusual. Moments before the disaster, the sky had glowed an eerie yellow and the air turned unnaturally still. It was dismissed as superstition until modern seismologists discovered these weren't just myths. Ancient Chinese scholars had been documenting a startling pattern for centuries, subtle shifts in weather that preceded earthquakes, observations now backed by cutting-edge science. Dive into the Hu Hanshu, a historical text from the 5th century, and you'll find meticulous records linking seismic events to atmospheric anomalies, sudden temperature spikes, unusual cloud formations, even bursts of light now recognized as earthquake lightning. One account describes winds rising from the ground days before a quake, matching modern observations of radon gas releases that can ionize air. Another notes well waters turning turbid, a phenomenon contemporary researchers attribute to underground stress disturbing sediment layers. These weren't random guesses, they were data points in the world's first seismic forecasting system, one that relied on nature's whispers rather than Richter scales. Modern science is catching up to these ancient insights. NASA QuakeSat mission and studies from Stanford University have confirmed that tectonic stress can generate electrical charges, altering the ionosphere and triggering infrared anomalies detectable by satellites. In 2008, cameras in Peru captured glowing skies hours before a major quake, precisely the dragon lights described in Ming Dynasty texts. Even animal behavior, long ridiculed as folklore, is gaining credibility. Labs in Japan have shown fish and rodents exhibit distress before quakes, possibly sensing subterranean vibrations or electromagnetic shifts. The real brilliance of Chinese forecasting lay in its methodology. Unlike Western traditions that separated meteorology from geology, Han Dynasty scholars treated the earth and sky as an interconnected system. Their cloud divination manuals classified earthquake precursors with the precision of modern field guides: wispy, horse-tail clouds signaling shallow faults, or sudden mists hinting at groundwater displacement. Some techniques were astonishingly specific. The Benkao Gangmu medical text advised watching for toads abandoning their ponds, a behavior now linked to pre-quake gas emissions poisoning amphibian habitats. Yet the most compelling evidence comes from repeatability. When the catastrophic Tangshan earthquake struck in 1976, survivors reported the same signs recorded 2,000 years prior: undrinkable well water, panicked livestock, and a sickly sweet odor now attributed to stressed rock releasing hydrocarbons. Contemporary geologists initially dismissed these accounts until satellite data revealed thermal spikes along the fault days earlier. The correlation was undeniable. The ancients had recognized patterns invisible to instruments. The implications ripple beyond history. Projects like China's earthquake weather monitoring network now blend traditional knowledge with satellite arrays, proving that sometimes the oldest observations hold keys to the newest science. As seismologists race to unlock reliable prediction, they're increasingly turning to these ancient texts not as curiosities but as untapped datasets. The past didn't just foresee our present, it left clues we're only beginning to decipher. The gleam of polished bronze in a Roman surgeon's tent wouldn't feel entirely out of place in a modern operating room. Archaeologists excavating Pompeii's House of the Surgeon uncovered a trove of 2nd century CE medical instruments so refined they could pass for stainless steel prototypes, bone drills with interchangeable bits, scalpels weighted for precise incisions, and forceps with ratcheted teeth designed to grip slippery tissues without crushing them. These weren't crude implements, they were specialized extensions of the healer's hand, engineered with an understanding of anatomy and mechanics that would take centuries to rediscover after Rome's fall. Take the terebra, a trephination drill used to relieve cranial pressure. Its hollow center allowed bone fragments to be extracted cleanly, while the sharp, fluted edges minimized heat friction, a feature modern neurosurgeons replicate with titanium bits and saline irrigation. The resemblance doesn't stop there. Roman bone levers used to realign fractures mirror today's orthopedic elevators, and their specular, vaginal, and rectal retractors employed screw mechanisms to maintain dilation, a principle still used in gynecological surgeries. Even the humble scalpel reveals startling sophistication. Surviving examples show tapered blades for layered tissue work and ergonomic handles carved to fit the surgeon's grip, anticipating 20th century studies on instrument fatigue. What's truly revelatory is how these tools reflect systematic medical knowledge. The Romans didn't just copy Greek designs, they innovated based on battlefield triage and gladiatorial wound studies. Archaeologists have found kits organized by procedure, with instruments like the Sciathyscus, a spoon-shaped probe for removing arrowheads tailored to specific trauma cases. This specialization parallels modern emergency medicine, where tools are optimized for speed and precision under pressure. Yet the most haunting parallel lies in sterilization. Roman texts like Celsus de Medicina insist on boiling instruments before use and storing them in vinegar or silver cases to inhibit infection, a crude but effective precursor to antiseptic protocols. Excavations at military hospitals like Valetudinaria reveal separate operating theaters with drainage systems, suggesting an early grasp of contamination risks. When Joseph Lister pioneered surgical sterilization in the 1860s, he was in many ways echoing practices buried for 1,500 years. Modern surgeons examining these artifacts confront an uncomfortable truth. While materials have evolved stainless steel for bronze, polymers for ivory handles, the core challenges of surgery remain unchanged. A Roman fibula surgical pin, used to stabilize broken bones, differs little in function from today's Kirschner wires, and their ligature needles for stitching vessels could pass for modern atraumatic suturing tools. The greatest divergence: anesthesia. Romans relied on opium and mandrake cocktails, a far cry from precision-dosed propofol, but their mechanical solutions were often eerily prescient. The legacy of these instruments isn't just historical, it's practical. Biomedical engineers now study Roman designs for resource-limited settings, where reusable bronze tools could offer sustainable alternatives to disposable plastics. In those carefully weighted scalpels and calibrated forceps, we see more than ancient craftsmanship. We recognize the unbroken thread of human ingenuity, stitching together the past and present of healing. Deep in the sweltering jungles of Mesoamerica, where jaguars prowled and ceiba trees towered, the Olmec civilization unlocked a secret that would take the modern world 3 millennia to rediscover how to turn sticky tree sap into bouncy, durable rubber. Centuries before Charles Goodyear patented vulcanization in 1844, these ancient innovators were already molding rubber into balls, sandals, and even waterproof coatings, using techniques so advanced they baffle chemists today. Imagine a society without metal tools or written language, yet mastering polymer science through raw experimentation, their knowledge passed down through generations like a whispered formula. The process began with the latex of the Castilla elastica tree, a milky sap harvested much like modern rubber, but here's where the Olmecs diverged from nature's raw materials. They didn't just dry the sap, they transformed it through a chemical reaction called vulcanization, the same process Goodyear would later claim as his own. By mixing the latex with juice from the morning glory vine, specifically Ipomoea alba, the sap underwent a molecular metamorphosis. Sulfur-like compounds in the vine's juice bonded with the latex's long polymer chains, creating a material that was elastic yet tough, resistant to heat and decay. Modern lab tests confirm this blend produces rubber with nearly identical properties to 19th century vulcanized versions, capable of bouncing to 80% of its original height. But the Olmecs didn't stop at chemistry. Their applications were staggeringly diverse. At the ruins of El Manotti, archaeologists unearthed rubber balls dating to 1600 BC, some as large as basketballs, used in the ceremonial ball game that echoed across Mesoamerican cultures. Other finds include rubber-tipped drumsticks, waterproof textiles, and even adhesives for hafting axe heads. The most startling discovery, rubber-lined containers that kept liquids fresh, hinting at an early understanding of microbial barriers, a concept modern science would formalize only in the 19th century. The true brilliance lies in the scalability of their methods. While Goodyear's process required precise sulfur ratios and controlled heat, the Olmec technique worked at ambient temperatures using locally available plants. Researchers at MIT recreated the recipe in 2011, noting how the morning glory juice acted as both a vulcanizing agent and a stabilizer, preventing the rubber from becoming brittle over time. This wasn't just trial and error, it was systematic materials science refined through centuries of observation. Why then did this knowledge vanish? Unlike Roman concrete or Damascus steel, Olmec rubber never faced extinction. Spanish conquistadors documented its use in the 16th century. But European minds obsessed with metallurgy dismissed it as a curiosity, failing to recognize its industrial potential until centuries later. The tragedy isn't that the Olmecs discovered vulcanization first, it's that the world wasn't ready to see it. Today, as we grapple with synthetic rubbers, environmental toll, petrochemicals, and pollution, the Olmec solution whispers an alternative. Biodegradable, renewable, and astonishingly durable, their rubber represents a road not taken, one where technology harmonized with ecology rather than exploiting it. In those ancient bouncing balls and waterproof jars, we find more than artifacts. We uncover a legacy of ingenuity that still has lessons to teach, if only we're willing to listen. From the celestial computer of ancient Greece to the nanotech steel of Damascus, these 25 predictions shatter our assumptions about the past. Was it mere coincidence that Hero of Alexandria toyed with steam power while Rome's concrete healed itself? Could the Maya's Venus tables and Zhang Heng's earthquake detector really be products of luck? The sheer weight of evidence suggests something far more profound. Flashes of insight surfacing across civilizations, separated by oceans and centuries, yet united by the restless curiosity of the human mind. Consider the eerie precision of these innovations. The Antikythera Mechanism didn't just track the moon, it modeled its elliptical orbit with gears. Damascus swords didn't simply hold an edge, their carbon nanotubes formed molecular armor. These weren't vague premonitions, they were working prototypes built by hands that grasped principles science would later formalize. the more we study them, the harder it becomes to dismiss them as accidents. Perhaps these cultures didn't just predict the future, they briefly touched fragments of it, their knowledge later scattered by time's relentless current. Yet the most tantalizing question isn't how they achieved these feats, but what else might be waiting to be rediscovered. For every Antikythera mechanism salvaged from a shipwreck, how many more lie buried? For every Baghdad Battery preserved in a museum, how many technologies vanished without a whisper? History isn't a straight line, it's a labyrinth of dead ends and forgotten shortcuts, some of which might still hold answers we've yet to uncover. So where does this leave us? In awe, certainly, but also with a renewed sense of possibility. These ancient visionaries worked without blueprints, without the collective knowledge we take for granted. If they could glimpse satellites and stem cells with nothing but observation and imagination, what might we achieve by blending their boldness with our tools? Now it's your turn. Which of these predictions stunned you the most? Was it the Roman concrete that outlasts our own, or the Olmec rubber that bounced centuries before Goodyear? Drop your favorites in the comments. I'll be reading every one. And if you're hungry for more mysteries where history and innovation collide, hit that subscribe button. Together, let's keep unearthing the lost threads of human genius, one revelation at a time. The past still has secrets to share, we just have to listen.